Okay, so welcome to lecture 3. We're going to record the lecture for the first time. It's kind of an experiment. I'll probably send an email about this, but what I'll do it because it probably will be very hard to see the writing on the chalkboard. So we're going to take high-def pictures of the chalkboard with Marcus's camera, and then we're going to post all that online so that you guys can watch the pictures. Okay, so actually, if you guys have questions, try to speak up so that, it's best. You have a question already? I haven't even started.
Yeah, no, last time.
Okay.
It's about Radboud's theorem.
Yeah.
It reads, as you said, it all symplectic manifolds of dimension 2n are locally symplectomorphic to R2n in some finite patch.
Mm-hmm.
So what does in some finite patch mean on top of locally?
Yeah, I mean, it means that it's not just like corrections. Let me think. It's not just the immediate neighbors, but it's actually some finite patch. So it's like what was it? Like in Riemannian geometry, if you look at the curvature and you want to show that it's locally flat, then you have corrections of order epsilon away that grow. So the point is that in this, it would be even the first order corrections are still small, yeah, or they're still zero. So it's only basically what I mean is that there are topological obstructions or kind of global obstructions to the theorem that you can apply locally for as long as you want, but at some point, if there's going to be some kind of topological obstruction, it's going to break down. That's about as rigorous of an answer you're going to get from me. But you can.
But for instance, the exercise with the harmonic oscillator,
Yeah.
the problem was you couldn't put in the zero because then it's.
The problem with the harmonic oscillator.
You did the coordinate transform from Cartesian coordinates to polar coordinates.
Yeah.
But then you have to leave out the zero because otherwise it's not
Yeah.
projected. Because
that's right.
Any angle with radius 0 is the same.
Exactly.
Okay.
But luckily in that
coordinate transformation.
Yeah. So
just the map is not bijective.
No, but that's a good point. If you're trying to map the harmonic oscillator phase space to a theta phi, you're going to leave out the origin.
Yeah.
But luckily, the origin in the classical theory, the origin is not that interesting, right? It's just a point with zero momentum. Yeah, zero momentum and zero energy. In the quantum theory, if you take out the origin, you could get effects from that, which I haven't really thought about for the harmonic oscillator. But if you take out a point in the phase space, quantum mechanically that can have some effects, and sometimes you have to. Sometimes your Hamiltonian is not even self-adjoint because you can lose the self-adjointness properties of operators and all kinds of stuff. But we're not going to be interested in really too much about the quantum theory. I'm just kind of flagging these things at the moment. This is just an 8-week introduction to canonical methods, and the idea is to kind of prime you to be able to use these methods in the quantum theory, or to use it to quantize general relativity or Yang-Mills. Okay, but we're not going to actually get to the quantization. But what I'm trying to do is flag various issues that could come up later if you take courses. Okay, that was a very good question. Yeah. Okay. And in fact, it does point out the limitations of Radboud's theorem. Yeah. Okay. Good. So let's start. Actually, what I wanted to do is quickly recap lecture 2, because I think that I got some feedback that it went quite quickly, and I think that's okay because for the first time through, the stuff seems very formal, and then the more examples we do, the more those examples will highlight the things. But lecture 2 and then the material in lecture today are going to be the formal basis for most of the rest of the course. So that's why it's important. And also because most of you aren't here, I decided to do a bit of a recap of last week's lecture so that we don't do too much new, and then focus on the rest of the stuff. Okay? Yeah.
Can you just give the reference? So if I missed the first lectures, I can look in books.
Like a book.
In books, yes.
Well, different books. If I can send you a link to the website where we have.
Yeah, I'll show you.
Yeah. Okay. So let's see. Let me start then. Am I still on the screen? Yeah. Recap. So the weekly recap of lecture 2. So, all right. What we did is we wanted to move from a Lagrangian picture to a Hamiltonian picture. And when we did that, we defined a Hamiltonian which was just a kind of Legendre transform of the action. So we wrote it as, the definition is Q dot. We define these phase space coordinates, which are transformations from the Q dots and the Q's to the P's. And then we define our Hamiltonian in terms of those new coordinates. And the specific definition we gave was Q dot alpha P minus L of Q dot alpha, and it depends, of course, on the coordinates, but we want to think of them as functions of the phase space variables. Okay, so that's how we defined our Hamiltonian, and then we said, okay, we realized that you can rewrite the Euler-Lagrange equations in terms of Hamilton's equations, and we found it convenient to define this notion of Poisson bracket. Hamilton's equations, in terms of this Poisson bracket, we can just write them as the time derivative of the Q's is just the Poisson bracket of Q with H. The time derivative of the P's is just P with H. And what we noted was that this Poisson bracket defines a natural a natural metric structure on phase space. So, well, in fact, this Poisson bracket is like the inverse. Geometrically, it's the inverse of a metric on phase space. And so,
In what sense?
Well, in a sense that I'm not going to define in detail in this course. In the sense that it's the inverse of the symplectic form, which is exactly the coordinates of the symplectic form are literally a metric in phase space. Yeah. In particular, you can just define these. So these Poisson brackets can just be defined through their fundamental relations. P alpha, Q alpha P beta equals delta alpha beta. And then the Poisson brackets of Q's with Q's and P's with P's are 0.
Can I ask you a question regarding those? That's you define the Poisson brackets to be like that, right? You can just do the whole definition starting from that first canonical bracket.
Yes.
So that does assume that the P's are totally independent from any Q's.
Yeah. Now we define this particular bracket structure. Okay, this is just our definition.
Yeah.
But the reason why we use this particular definition is because we can write Hamilton's equations this way. So the point is that there's a it's the variational principle that we're using in the action that is suggesting a particular choice of symplectic form on the manifold, so a particular choice of metric structure on phase space. And it's that metric structure where the solution of the theory is actually traced out by the flow of these constraints under that metric structure. And so so basically this Poisson bracket is related, the definition that we use is related to the original variational principle that we have, and you're not completely free. So
So what I'm saying, I guess what I want to ask is that definition holds regardless of how you actually define the p beta alpha as in terms of the configuration space variables, right?
Yes. So the answer is that this definition is very closely tied to the Legendre transform that you perform. And in particular, it's also tied to the invertibility of the Legendre transform, etc. So I know where you're going with this, but I think we should discuss this later. But yeah, it's... Yeah.
Because, I mean, so for example, when we invert when you write P in terms of Q and Q dots, it's still the case that a lot of times the P's will be functions of the Q's, not only the Q dots.
Yes. Yeah.
And however, when you're writing the Poisson brackets in terms of derivative with respect to Q, you write dP dQ equals 0. And so you're really assuming that they're completely independent from that point on. Yes. Okay.
That's right. Yeah. So the question is, so there are some theories, I know where you're going because we
had a discussion.
Yeah, there's some gauge theories where if you make this canonical choice, it might not match with the variational principle you're trying to implement. But these are technicalities that I'm actually not that much of an expert in.
So you just take that for definition and roll with it.
For the purposes of this course, we can assume that this metric structure is coming from the variational principle that we're imposing. And that was what I wanted to emphasize with the lecture last week, in the way I derived it, that it's something that's actually coming from the variational principle itself. Okay, now this particular bracket, I already kind of said this today, defines a vector field with respect to some arbitrary phase space function. And if I keep free what this vector field is acting on, then I can think of this as a directional derivative. So literally this vector field is defined as the Poisson bracket of whatever it's acting on F. And this tells you, using the geometric picture that I just gave, this tells you it's completely analogous to taking a directional derivative on phase space in the direction of F. Okay? But because So now that we have these vector fields, it's clear that the Hamilton equations are just the vector fields generated. The classical evolution is just the flow generated by the vector fields of the Hamiltonian. And that's a very nice geometrical picture to have in mind. Okay, so we have phase space, and then we have some classical solutions, and the claim is that this Legendre transform is convenient because if I use this particular symplectic structure, I'm guaranteed that the solutions are just generated by the flow of the Hamiltonian using this particular structure, okay, metric structure. Good. So that was just a really quick review. And I think the reason why I'm doing it to you is because these words are probably not familiar to you. So the more I say them, the more you'll remember. And the more times I draw that picture, the more words you'll be able to link to the picture. And then eventually you'll start talking as if it's a part of your language. Okay? So now what we saw immediately after that, I didn't actually prove it, but we proved like I kind of sketched out how you can prove some limit of it in the assignment we did in the exercise class. But effectively, you can use variations of that to prove the thing more generally, which was regarding the question that you asked. So this is Radboud's theorem, and it's a very powerful theorem, as we saw, because it allows us to talk very nicely about the geometric properties of constraints on phase space. And those constraints are well, the whole point of the course is to talk about the Hamiltonian dynamics of constraint systems. And so this is why this thing is particularly helpful for us. Now, the theorem was, I might have stated it differently, but all symplectic manifolds are locally symplectomorphic to R2n, where n is the dimension, in a finite patch. And in particular, we saw in the harmonic oscillator case, as was brought up in the question, we saw that this theory does fail for some traces of canonical. Actually, in that case, it's not a symplectomorphism because I think that's what you said, because it's not one-to-one. It's not a smooth map. But anyway, we okay. So now here we introduced a bunch of terminology, and it might be useful to refresh what the terminology was. So I said a symplectic manifold was any is just a manifold with an invertible Poisson bracket. So if you can define the Poisson bracket and then invert it, then you get something called the symplectic form. It's just the inverse of this. But if you have a manifold with a symplectic form, then it's a symplectic manifold. So for the purposes of the course, it's only really important to realize that there's a relationship between symplectic structure and this Poisson structure. And in the cases where you can do this inversion, then you have a symplectic manifold. And so the theorem is just for symplectic manifolds. But
can I ask you some
yeah.
kind of naive question? And it's something I've heard about several times. I'm not exactly sure.
Yeah.
So I've seen cases where people started thinking of the configuration space, it's just position space, as just a manifold.
Mm-hmm.
Then they define all the velocities as being the tangent bundle,
Yeah.
and then they showed how the phase space can be, the general transformation can be seen as a map from the tangent bundle to the cotangent bundle. So is it always the case that tangent bundle, all symplectic manifolds can be seen as some cotangent bundle of some manifold, or the other way around?
Is it true that all symplectic manifolds are a cotangent bundle? I don't know. I mean, it depends on whether you can invert the adjoint. So I want to say probably not, but certainly the other way. So every time you have a cotangent space, if you know how to define the adjoint, then you can define. I guess it's related to gauge theories, right? If you have a theory with redundancies and you don't know how to invert the adjoint.
Yeah.
I this is really a bit out of my depth.
But there is some connections there.
Sure. Of course,
Okay.
Yeah. But let me. So we're going to come back down to earth in a second, but I said the word symplectomorphic because it sounds really fancy, but it's just it just means up to canonical transformation. And canonical transformations are really important. And what are they? Canonical transformations are coordinate transformations. So this should be smooth, probably. Smoother than one-to-one. So in that case, the polar coordinates is not an example. Coordinate transformations that preserve the Poisson structure. Okay. Now the key thing was that we saw examples of this, and we didn't prove it in general. But these canonical transformations are important because they leave the equations of motion invariant. You can see that already from the fact that the Poisson structure is defining the Hamilton's equations. So, of course, if the canonical transformations preserve the Poisson structure, you won't expect it to locally affect these equations of motion. But they can redefine the Lagrangian up to a boundary term. So that's kind of important, is that these guys, they leave the equations of motion invariant because L goes to L plus some time boundary term. Okay, and this means that the stationary condition of the action is invariant. So we're safe to do canonical transformations without affecting the local equations of motion. The way I think of it, a canonical transformation is a rearranging of the physics. It's a rearranging of how I feed physical information into my variational principle. I'm just redefining the things that I mean. So if I want to say I have an electric field and I do some canonical transformation, I have to figure out a way to communicate the information about the new field into my variational principle. So it's just a reshuffling of degrees of freedom. Okay. And this boundary term is basically just changing what's held fixed on the boundary. So when you do this variational principle, you pick up a boundary term, and the boundary term tells you the things that you have to keep fixed on the boundary. This thing just shifts that. This boundary term just changes, it rotates what should be fixed on the boundary, and that just means that you're fixing some other part of your phase space. Okay. All right. Good. So, what were the consequences of this? Now this is a very powerful theorem, because now what we can do is we can say that you can always choose a set of coordinates on your phase space that will be local coordinates, but they will probably be able to be good enough for a classical evolution. That will transform any flow, so this could be the flow of any function, into straight line flow, trivial flow. So I can always do a canonical transformation that will turn these curved things into straight lines. And then this would be the flow of some vector field, this would be F, and the flow is always in a direction perpendicular to F, which is the momentum. So the idea is that the vector field generated by F will always generate flow in the direction of the momentum conjugate to F. And the nice thing is that this is via Radboud, and you immediately get Hamilton-Jacobi theory. So you immediately know that if F, so an example of this is if F is the Hamiltonian, then you clearly have a conserved quantity because the Hamiltonian is preserved under its own evolution if it's time independent. But also you, you can see that this H acts trivially on the phase space variables. So it just changes. In this case, the PF is time. And you're generating some time evolution, which doesn't affect any of the variables. So there exists always, through Radboud's theorem, a canonical transformation that will make it so that your variables don't ever change in time. And that's the basis for Hamilton-Jacobi theory, which is also the closest classical formulation to quantum mechanics. So I just wanted to highlight that because I think it's very powerful way of thinking about classical mechanics. And it also highlights the power of Radboud's theorem. So we're almost done our, now, then we said, okay, we assumed that the Legendre transformation that we used to define our Lagrangian was invertible. And what happens when it's not anymore? So what happens when the rank of the Hessian, and we define this as it was the invertibility condition for the momenta in terms of the coordinates. So it was literally dp alpha dq dot beta. When the rank of this thing is less than the dimension of the configuration space, then you have a problem because you can't invert the p's directly for the q's. And so we were calling this thing n, and we were calling this thing, m, we're calling this thing n. And so when m is smaller than n, then you have a problem with the invertibility. And in particular, what it means is that there are relationships among momentum. So the map between p and q is not one-to-one, and you get a bunch of constraints. And the constraints have the number of linearly independent constraints is just equal to the difference between the dimension of the configuration space and the rank of the Hessian. Okay. Now, basically the rest of this lecture, we're going to try to talk about a procedure that was first developed by Dirac, but then we're going to talk about slight tweaks to this procedure, which is to figure out, essentially the purpose of the procedure is to figure out the rank of this in an algorithmic way, and then identify these constraints, and then use them to fix the underdetermination problem. So the problem here was that if we're talking about flows on phase space, we don't know how to map the p's to the q's because the p's map to several different q's. And so there is a underdetermination in the what was I saying?
You cannot express the q dots.
Yeah, you can't express the q dots in terms of the p's. But this was a result, we went through this. This was a result of the fact that there is a underdetermination of the physics. That somehow the physical information that we use to vary the boundary doesn't fix the q dots explicitly. And so then we have to come up with, and the procedure is to figure out a way to resolve that underdetermination. So that's going to be the point of the rest of this lecture. Okay. And we started on a special case of this, where it's relatively straightforward to figure out what's going on. So, so this is case 1. Okay, so the idea is I'm going to go through different cases, explain what they are, and then at the end I'll explain Dirac's algorithm for identifying the cases and how to implement them. Right? So that's the pedagogy I'm going to try to use. So the first case is when the constraints Poisson commute. So suppose you've already identified some constraints. Okay. The idea is, well, okay, perhaps, okay, so the first situation is if these guys weakly commute with the Hamiltonian, which means that they're equal to some linear combination of the constraints. And we use this symbol weakly equal to 0 because you're saying that it's only 0 on the constraint surface. And not only do these constraints, in this case, commute weakly with the Hamiltonian, but they also commute weakly with each other. So in this case, you have what we call a first-class algebra, or first-class constraints. Okay. Now, in this case, we can just use Darboux's theorem to find a set of coordinates which trivialize this algebra, which basically abelianize it. So, what does that mean? It means that we can invoke Darboux and say there exists some canonical transformation, and I can come up with a precise procedure for doing this that's formal. And then if I actually have to solve for this, I can't, and that's the whole reason why we do gauge theory in the first place. But formally, there exists a procedure which is well defined, at least locally in phase space, that will allow me to decompose my phase space functions into coordinates which are exactly the constraints and their momentum. Q I now, and I'm calling this the reduced coordinates. And then the momenta, pi I, and then the reduced momenta. And in this coordinate system, these guys are just canonically conjugate, and they Poisson commute with these things. Okay? And they Poisson commute with each other. So you immediately have that there exists a coordinate system where this is 0. Moreover, because I can pick the Hamiltonian as one of these coordinates, I can easily see that these guys also have to commute with the Hamiltonian. And I'm only allowed to do that because these guys are weakly equal to 0. Okay? And we'll see case 2 is when this basically, instead of having, in this case, instead of having this being proportional to constraints, they're going to be proportional to phase space functions or just constants or whatever. And then you're going to not be able to use Darboux's theorem because Darbo's theorem is only for canonical transformations. And the canonical transformations can't change the symplectic structure. So there's no, here I can do a canonical transformation that will basically make this 0, because this is basically 0 on the constraint surface anyway. But yeah, it won't work in that case. And that's where we have to get more clever. Yeah.
So that would be an example. That canonical transformation would only be canonical on the constraint surface, I guess. Because then outside of it, then the brackets won't be 0. But on the constraint surface, they are.
Yeah, but no. So that's not. I think that you can.
No, but they are still. I mean, satisfying the symplectic structure. I mean, outside the constraint.
Exactly.
Proportional to the constraints.
So outside the constraint surface, the constraints are not 0. And
but the algebra is still preserved.
No, but the bracket really means that if you have two different canonical variables, their bracket is 0. And if their bracket gives you some other constraints, on the constraint surface it's 0, so it's really preserving the canonical structure. But not outside of it.
But the point is, even if you are outside the constraint surface, you can come up with a canonical transformation, and that preserve that algebra instead of this proportional to a constraint. And then, let's say, project it out on the constraint surface when it goes to 0.
It's not. So the thing that is clear is that on the constrained surface you can do this, and there's all these coordinates can be made to be independent.
Yeah.
Okay. And that's all that matters for us.
Yeah. So
At the
the question would be, why would we care outside of the constraint surface anyway?
Exactly. But anyway, that's yeah. So so this is the statement that you've got. I already drew this. Oh yeah. So the picture behind this was that now you can think about these flows. Here I have a constraint phi, and then I have its momentum pi, and we can find a coordinate system where these flows are completely straight, they're trivial. But moreover, the flow of the Hamiltonian is in some direction perpendicular. And perpendicular means that, at least on the constraint surface, is perpendicular. So it's perpendicular in the sense that it Poisson commutes with this. So that's what I mean by perpendicular. Again, I'm using the symplectic structure as a metric. So this is great because it allows us to say, well, actually, the Hamiltonian is only now acting on this reduced phase space, and these flows are completely trivial. Now, what are these pi's? These are the directions which are not fixed by the physics, right? That's the interpretation. You can see now right away that the underdetermination problem comes from the fact that we have physical information on the reduced phase space, and our Hamiltonian is only evolving these guys. Our Hamiltonian is not evolving these guys. And so in order to understand, in order to be able to get a well-defined evolution problem, we need to specify some arbitrary evolution for these guys. So our Hamiltonian itself is not flowing on these guys. But if we want to make our theory fully predictive, when we're working on the larger set of variables, then we need to specify arbitrary information, which is the location of these guys. And these guys are called the gauge directions. Okay. And it might be more conventional to think of this guy as the momentum, and this guy as the coordinate, and then this is a coordinate. But it doesn't really matter, it's just a convention, what we want to call P and what we want to call Q. So what is Dirac's proposal for how to fix the problem of not knowing how to specify these guys? Well, his fix is to say, I just arbitrarily assign values to these. So I call these guys, and he gives a very particular prescription. He says, instead of thinking about the flow of the Hamiltonian, I want to think about the flow of an extended Hamiltonian, which acts on here. And this extended Hamiltonian, all it does is it just moves these in arbitrary directions which we specify. Okay? So he says, okay, let's consider this Hamiltonian, but to fix the underdetermination, we're going to add arbitrary functions that are Lagrange multipliers, multiplying these constraints. So in some sense, it's clear that on the constrained surface, the flow of these guys is going to be zero. That this Hamiltonian is going to be acting on the coordinates in the same way as this Hamiltonian, because these guys are zero, and the flow of these guys is zero on the constrained surface. And in fact, well, you can see that pretty clearly. I think I even did that calculation in the notes. If I look at these, the constraint itself, well, the constraint itself is obviously preserved because it commutes with the Hamiltonian and it commutes with itself weakly. So this is weakly zero, but also in the Darboux coordinates anyway, we see that the flow of these guys is just, well, it commutes with h in these coordinates. It commutes with h, but then it doesn't commute, obviously, with the constraints. It's conjugate to the constraints. I should put a j here. So you just get delta ij, which gives you lambda I. So it tells you that the time derivative of the pi's is just equal to these arbitrary constants that you fixed. Okay, and that's what how he fixes it. He says, okay, if I add these arbitrary functions, then I get a well-defined evolution problem. Okay. That's for first-class constraints. What about now I want to kind of motivate the second case by pointing out an example which is kind of relevant, I think, or important. So there are these canonical gauge fixings. So the word canonical in English, it's kind of an old English word. It means standard. It means like, canonical means like the classic thing that everybody uses. And so canonical is actually another word for saying some kind of preferred gauge choice. And it's really weird that in this literature, the word canonical is applied to the, is used to kind of represent the canonical structure, which is the phase-space structure. So I guess at some point somebody thought that this structure was so basic and fundamental that it was the canonical thing. But then it kind of gets mixed up with the normal usage of the word. Yeah.
Is the obvious better word for it? Like the obvious choice.
The obvious choice, yeah, like standard, the canonical, yeah, absolutely.
Because every time in mathematics something is a canonical transformation, and it's just the only thing you can point out, the only reasonable choice.
The only reasonable one, yeah, it's a canonical choice of coordinates or canonical, yeah. And so somehow phase space is so basic, so fundamental to physics that people were calling it canonical. Anyways, kind of a side note. Gauge fixing. And maybe, I don't know, how long have I been lecturing for?
2:35.
2:35. Okay, so I'll do this, and then I'll break, and then we'll take up stuff next. Case 2, after the break. So in the canonical gauge fixing, it's just, there's a really obvious choice here, which is just to pick lambda equals 0. It's pretty obvious. And if you have lambda equals 0, then it's just saying that the gauge coordinates are constant. So you can think of this, the picture of this is that you have some kind of gauge fixed surface, and you have these orthogonal, these are called gauge orbits, the flow lines. They're gauge orbits because they're parameterizing directions that are unphysical. And then you can say, well, I pick a canonical gauge fixing, which just makes these guys constant. What does that mean? It means that I pick a surface, pi equals constant, right? So this is obviously a surface, pi I equals constant. Well, I'm drawing it, it's not obviously, it's just telling you that's what it is. So you imagine that there's a surface in phase space, which is this direction that's conjugate to the constraint, and then it cuts it at exactly a 90-degree angle. Well, I'm using the word 90-degree angle in a kind of, it cuts it orthogonally, but it's not orthogonal in the sense that there's no flow. It's orthogonal in the sense that it's exactly matching. So it's orthogonal in the sense that this constraint, this is the constraint, and this is its momentum, and they're canonically conjugated. So the gauge fixing surface, pi I minus constant equals 0, is just exactly conjugate to the constraint. So it's orthogonal is maybe not the right word. It's not a tangent direction, it's a complementary direction. So maybe the word, maybe this is the wrong, it's somehow complementary. It cuts it in exactly one place, but in a straight line. So, right, there's two different notions of orthogonal. There's when this bracket is this, and then when this bracket is 0. So I don't really know how to distinguish between the two. But anyway, you can see that this is the canonical choice of gauge fixing because it has this very simple structure. What we'll see is that these gauge fixings have really nice properties. But there are also, of course, more general things that you can do. You can have more complicated constraints. You can have some arbitrary function of the pi's. Maybe not completely arbitrary, but it's arbitrary enough that this thing is still non-zero, that it still intersects. So you can pick other gauge fixings which will cut like this and be defined from some more general surfaces. But then we're constraining our dynamics to lie on this surface, and this surface won't have anymore a nice Poisson structure. So then the question is, okay, now how do we take that into account? So there's a procedure by Dirac that works in the classical theory that allows you to deal with this kind of projecting the symplectic structure onto this phase space. So I'll go into that in the next 45 minutes. Okay. So that was
So,